Right then, so this is really kind of an odds and ends type lesson for aromatic chemistry. We've done the majority of it, but it is important, especially this bit. Um, so when we talk about nitration of benzene, one of the things that often follows on from that, it wasn't in my previous video, but one of the things that often follows on from that is the reduction of nitrobenzene. So again, here are the facts, right? You can take nitrobenzene or some similar nitrated arene and you can reduce it to an aromatic amine. The reducing agent is a mixture of tin and concentrated HCl, and you would probably, heat it in that mixture, possibly under reflux, in order to get the reaction to go. Aromatic amines can be used to produce dyes and polymers and some other stuff too, but the main kind of use that you're supposed to be aware of is that they are used in dyes. So let's have a little look at how this reaction works. We don't do a mechanism for it, we just have a look at the equations. So I've done two versions, one where I've shown the sort of skeletal nitrobenzene and the skeletal phenylamine, and then one where instead of it being shown as a kind of skeletal structure, we've got the molecular formulae. So the molecular formula version is probably a little bit easier to try and balance. Okay. The first thing to point out is we've got two oxygens in the nitro group. That's going to then have an impact on the water, which is then going to have an impact on the hydrogens. So have a go and see if you can balance it. Notice that we've got H in square brackets representing the reducing agent. That's common notation which you've seen before when looking at reduction of carbonyl compounds. So we're going to need 2 moles of water because we need lots of oxygen atoms on the right hand side. That then means that we need 6 moles of the reducing agent. If you're wondering where the 6 comes from, there are 2 hydrogens here and there are 4 hydrogens here. I'm ignoring the hydrogens that are actually in the benzene ring, these 5, because there were 5 on the left and 5 on the right, so we don't really need to look at them. So 6 moles of the reducing agent. So that's a little bit weird, it sometimes throws people, and it would be the same in this version. Something to watch out for: if you've got 1,3-dinitrobenzene, right? Let's say that you boil it under reflux, heat it under reflux, with the tin and conc HCl mixture, then it's reasonable to assume that you could get 2 amine groups. So again, you have to be a little bit careful with this, right? It's very easy to just put 6 moles of the reducing agent in, but if you're thinking carefully about it, then you'll realise, well, actually, I need 4 moles of water, which is giving me 8 hydrogens, plus another 4 from the amines, which means 12 moles of the reducing agent. And obviously, if you've got a trinitro, it's going to be 18 moles of the reducing agent. So it's always multiples of 6, basically. So that's something to watch out for, okay? And actually this links to the next thing we're going to have a look at. So what I'm going to say is that from here on, it starts to get a little bit silly in terms of difficulty. Just to clarify, in the aromatic topic, the hard questions are not really the ones that are about the aromatic chemistry. If it's a nitration of benzene question, it's probably pretty straightforward. If it's a Kekulé question, I suppose it could be a bit trickier. I talked about dienes and stuff like that in that lesson. But the real challenge in the aromatic topic is something that AQA absolutely love doing, and that is they give you reactions of functional groups that are attached to benzene. So let's have a look at what I mean. If you react just a plain old benzene ring with ethanoyl chloride in the presence of an aluminium chloride catalyst, keeping water away and making sure that it remains dark, you will get an acylated benzene product. Phenylethanone. So that is kind of, I don't want to say it's straightforward, but it's what you'd expect to happen, right? the reaction is happening at the benzene ring, you're getting this acylation, you'd anticipate that that's something you'd find in the aromatic topic. But let's just think about something else. What about if you take phenol, hydroxybenzene, whatever you want to call it, the aromatic alcohol, and you react that with ethanol chloride? Well, the fact that it's aromatic doesn't really matter. It's an alcohol. That's the way you're supposed to view it. And so if you react it with ethanol chloride, it's the same. Well, you can imagine it as the same as if you react ethanol and ethanol chloride. In other words, right, what you're going to get is an ester, right? So I guess we'd call that phenyl ethanoate. Okay? In this case, the benzene ring being there makes no difference whatsoever. I mean, it probably will make a difference to the rate of the reaction and various other factors, but what I mean is, it's not the benzene ring that's reacting, it's the OH group. AQA love this stuff. They love throwing in synthesis pathways where maybe one of the reactions is a nitration or, an acylation or something like that. But then the rest of the reactions, even though there's a benzene ring present, it has nothing to do with them, right? Let's have a look at some more examples. Thinking about aromatic amines, if you nitrated benzene, then reacted it with tin and conc HCl to reduce it, you could get phenylamine. Again, that would react with ethanol chloride, and it wouldn't necessarily be anything to do with the delocalized ring of electrons. In this case, you're going to get an amide, right? Again, nothing to do with the benzene ring. This could just as easily be ethylamine and ethanol chloride. What about this? We started with the example of phenylethanone right up here. That's phenylethanone there. What about if you take your phenylethanone and you react it with a reducing agent, right, which you might have to name? Or what about if you react it with acidified KCN? This, again, is completely ignoring the fact that the benzene ring is there. You're literally just looking at it as if it's a carbonyl compound, a ketone. So if it was a reducing agent that you reacted it with, NaBH4 in aqueous solution, then you would essentially get a secondary alcohol, right? If you reacted it with acidified KCN, then you would get a hydroxynitrile. All of this stuff is from earlier in the kind of year 13 organic chemistry topics. And you could name and outline a mechanism for each one of these. And if you want to challenge yourself, then what you would do is do that. You'd look at every example I've given you so far, and you would practice naming and outlining the mechanisms. I'm not going to, because it's beyond the scope of the video, really. I'm just trying to sort of point out to you the kinds of things that AQA do that make people mess up stuff in the aromatic topic. What about this one? This time, what we've got is essentially a halogenoalkane attached to a benzene ring. There are three things we could look at here: an excess of ammonia, cold aqueous sodium hydroxide, or hot ethanolic potassium hydroxide, for example. It doesn't matter that I've changed from sodium to potassium hydroxide. It could be either of those. They're interchangeable, really. So again, this is all year 12 stuff from the halogenoalkanes topic. Can you name and outline the mechanism for these? Can you, deduce what the products are going to be? So with the excess ammonia, right, we would anticipate that we get an amine, Okay. With the cold aqueous sodium hydroxide, we would anticipate that we'd get an alcohol. Both of those are examples of nucleophilic substitution reactions, right? Then with the hot ethanolic potassium hydroxide, we would anticipate that an elimination reaction would take place. Made a mess of that. And you would actually end up with an alkene, right? So you'd end up with phenylethene. So there's a lot going on here, right? It's anticipating that you can connect lots of different topics. But the AQA love this. They love putting a benzene ring into these synthesis pathways because they can do one section of aromatic chemistry and then they could do a load of other things that just look really, really hard and horrible, but in reality are relatively simple, actual single steps. It's just that as soon as the benzene ring is there, students just really struggle. What about this? Let's say that you did have an alcohol, right? And you mixed it with conch sulfuric. What might happen? Again, in this case, what we'd anticipate is you get a dehydration reaction, the elimination mechanism, and you're going to get an alkene. Okay. Again, trying to cover a lot of different stuff. This time we have an aromatic ester. You could hydrolyze this using conch sulfuric or using conch sodium hydroxide. So think about the esters topic. What would your products look like? So if you used conch sulfuric, you can have a carboxylic acid. And you can have methanol. If you used alkaline hydrolysis of the ester, you're going to get the salt of the carboxylic acid and the alcohol. So there's a lot going on here, right? It's very, very easy to kind of get messed up with all this kind of stuff. So then, this is the sort of last section, right? And it, like I said, if you've by now, realistically, if you're not bothered about challenging yourself and trying to kind of achieve a top grade in A-level chemistry and improve your depth of understanding, by now you've pretty much tuned out, and that's fine. You could have stopped the video by now, it doesn't matter. All right. This is something that is not on spec, which is Friedel-Crafts alkylation, not acylation. But stuff not being on spec does not stop the AQA from asking questions about it, usually justified by them giving you a bit of additional sort of scaffolding. So alkylation occurs in a very similar way to acylation. If we have a look at this example, I'm saying that we've got some chloroethane and it can react with aluminium chloride, so it's the same catalyst, and it can make an electrophile, and it'll make a positive ion and a negative ion. So pause the video if you feel like challenging yourself, have a go at deducing these structures. What we should wind up with is this ion and same kind of idea again, AlCl4-. So that's exactly the same kind of relationship as what you get in the acylation reaction. If you feel like having a go at the mech, I've set it up for you there. It's exactly the same electrophilic substitution mechanism. So we should have curly arrow from the ring towards the electrophile, curly arrow from this pair of electrons in to reform that broken ring, and we should have an H plus here, which is then going to regenerate or help regenerate the catalyst, and we now have ethyl benzene. So we've alkylated our benzene ring. Instead of acylating it, we've alkylated it. So one of the hardest questions that I've ever seen about this was, the wording wasn't like this, but it was essentially saying, if you start with ethene and benzene, can you outline a two-step synthesis to make ethyl benzene? So we've just made ethyl benzene, but this is saying if you start with ethene and benzene. So again, if you want to challenge yourself, think about this. You do actually know all the stuff that you need to answer this. It's just that you might not know that you know it. So if you've had a go, you can react ethene with hydrogen chloride. The mechanism here is electrophilic addition across a double bond. That'll make chloroethane, which is what we needed in the previous example. Your chloroethane can then be reacted with aluminium chloride under anhydrous and dark conditions, and the electrophile that you get from that reaction can then be used to make ethyl benzene. So again, that's a tough question, right? It's difficult. So last little bits, again, pure challenge, right? What I want you to do is, using similar sort of logic that we've just used for the previous alkylations, show me how 2-phenyl propane can be made, and that's the structure of that molecule underneath. Compare that with the synthesis of propyl benzene, and I want you to explain in as much depth as you can the similarity and differences between these two syntheses. So pause the video and have a go at that if you fancy pushing yourself. So then, to make 2-phenyl propane, we're going to react propene with hydrogen chloride, right? And for it to make the desired product, the mechanism is going to need to proceed like this, where the chloride ion attacks the middle carbon. Okay? In other words, the mechanism needs to proceed via a secondary carbocation. That's then going to make 2-chloropropane. The reason that you need to do that is that your 2-chloropropane needs to react with your aluminium chloride catalyst and make the positive charge be on the central carbon. Then, I've not drawn the mechanism in full, but you can see that you end up with 2-phenyl propane. So if you're going to make propyl benzene, let's say that we have electrophilic addition again, but this time mechanism proceeds via a primary carbocation, and you're going to make 1-chloropropane. That can still react with the aluminium chloride to make the electrophile, but because of the location of the charge on the electrophile this time, having lost the chlorine from a different carbon, you're going to make propyl benzene. So really, in terms of like what you should be thinking about to do with comparing these reactions, they're the same reactants, right? Same reactant mixtures. If you were just mixing all this stuff together, you'd be more likely to get 2-phenyl propane than you would be to get propyl benzene. And that's because in the initial step, 2-chloropropane is the major product because it proceeds via a secondary carbocation, which is more stable due to the positive inductive effect. That positive charge is spread over 2 carbons on either, well, 1 carbon on either side, instead of being located at the end of a molecule. So there it is at the end, less stable. There it is in the middle, more stable. So that's a nice link. Again, we're looking at something here that is very unlikely to be asked about, but it's the kind of thing that would make a really, really nasty paper 2 question. I think that's enough for now.